In this video, you will see very important part, haloalkanes and haloarenes. Now haloalkanes, they have general formula Rx. Haloarenes, they have general formula ARX. Here you know R dash, it stands for alkyl group. It stands for alkyl group. Like if we have CH3, here one bond is free. So this is called as methyl group. If we have C2H5, so it is called as ethyl group. Similarly, in case of aromatics, if we have C6H5, so this is phenyl group. So this is the basic introduction about the alkyl and aryl halides. Now coming to their common names. Common names in general. So the haloalkanes, they are called as alkyl halides. They are called as alkyl halides. Alkyl halides. If I write here CH3Cl, so this is called as methyl chloride. This is methyl chloride. Similarly, in case of other like C2H5, this is called as ethyl bromide. This is there. Similarly, in case of others, we do naming like this, common system. So this is methyl means alkyl, halide means chloride, bromide, iodide, similarly. So this is there. Now coming to aromatic side, if I write here C6H5, so this is having this C6, 5, phenyl, this, and so actually in aromatics there is slightly change. We don't have that. So here it is called as chlorobenzene, brombenzene, iodobenzene, all are same. So here, as I have written phenyl, so we don't write phenyl. It is relaxation in case of aromatic compounds, and here is chlorobenzene, like Cl, and then this. Here, if I write Br, so it will be bromobenzene, not phenyl bromide or like that. So this is about the general introduction about the common name and the simple ways now this. Coming to IUPAC nomenclature or scientific naming. So as you know, haloalkanes, they are called haloalkane. So this haloalkane, it is made up of two segments. One is halo and other is alkane. Halo part and alkane part. So corresponding alkane has to be taken into consideration. If I write here simplest, they say CH3Br. So here this halo is prefixed. Here halo is prefixed, and this alkane is suffixed because it is halo is weaker. Halo is weaker. X, it is having the less tendency than that of the carbon, and so this is the probability. So this is CH3Br, so it will be bromomethane. If I write here C2H5I, so it will be iodoethane. So simplest way, it has to be written. If there is some change here, like if I write here CH3CH and here CH3, so here I write here Br. So here as it is prefixed, so here we write numbering 1, 2 and 3. So it comes at 2. So it will be 2 bromo 2-bromopropane. 2-bromopropane. And see this. Again, I am going to divide. This is prefix. This is water and prefix. 2-bromo. Here it is there, and this is suffix. N is suffix. Pro means 3 carbon, and so this is there. Now we coming to aromatic. So here in haloarenes, it is in both the systems. This is chlorobenzene. No other initiate as well as in common. Both are same. Chlorobenzene, bromobenzene, iodobenzene in both the systems. A relaxation has been given to this aromatic. But if there is some addition, that if there is 2Cl, so here is 1, here is 2, or 1 or 2, everything. So this 1,2 dichlorobenzene, 1,2 dichlorobenzene. If it is substituted by something else, if here I draw, if it is OH, here it is Cl. Now it is dominating. OH group is dominating. It is stronger than Cl. So here it will be 1, it will be 2. So it will be 2-chlorophenol. Similarly, like this. If we have this type of compound here, if I put here Cl, so here COOH get one position. This is 2, this is 3, this is 4. So it will be 4-chlorobenzoic acid. So this is about the naming, this is about the nomenclature, just simple all the basic rules. Now coming to classification of haloalkanes. So haloalkanes, they have been classified into 3 categories. First is primary haloalkanes. So primary alkanes, they are the haloalkanes in which the primary carbon bears this halogen or halide ion. So when halide ion is at the primary carbon atom. A carbon is said to be primary when all the 3 valencies are satisfied by adjoining hydrogen. See here, this having the X, this H. So this carbon is primary carbon. So primary carbon has halide, so this is primary haloalkane. Now coming to secondary haloalkane. So when the secondary carbon, and what is secondary carbon? When the 2 valencies of a carbon are satisfied by adjoining carbon or 2 by hydrogen, both, either by 2 adjoining hydrogen or by adjoining carbon. So here, if I write here like this, and if it is CS3 and this is there. So this is here. So in this carbon is said to be secondary, this carbon is primary, this carbon is primary. So this is the secondary, 2 by the adjoining, or if you write like this, C. So this is there. This is the secondary haloalkane. Now coming to tertiary haloalkane. So tertiary. What tertiary? All the three valencies are satisfied by adjoining carbon. See here, if I write here this carbon, so This is having X. So this carbon is again primary, this again primary, this again primary. This carbon, this carbon, this carbon. All the three. It is said to be the tertiary haloalkane. Now coming to next important part, nature. So haloalkanes and haloarenes, they have distinct nature. Here just I am going to mark here a line. This is about the haloarenes. Now haloalkanes are distinctly polar. They are distinctly polar in nature. Means they are water soluble and they exhibit such reactions on which there is addition of nucleophiles for aging. How it is possible? If I put here the C and here is X, you know what is there? Halogens have very strong tendency to withdraw the electron pair. So electron or electron pair or bonded electrons between this carbon and this halogen will be attracted towards or it will shift toward this. As a result, it will have delta negative charge. As electron density between this carbon and this halogen will be shifted towards this because of electron withdrawing nature. So when it has negative charge, so of course this carbon will have delta positive charge. So as a result, see, same molecule has this polar charge, polar nature, and they have the charge. So thus they are distinctly polar in nature. Now coming to haloarenes, so this haloarenes, this is the benzene ring. Actually, benzene ring has tendency to withdraw the electron towards itself, just opposite to that. And as a result, this is also having a strong tendency. So what happened? There is no polarization of charges. And as a result, they are not polar nature. They are water insoluble. Unlike haloalkanes, so due to this polar nature, they exhibit different properties, they exhibit different features, and so this is about there. And so this decides a lot about the nature, about the character, about the chemical, about the physical properties. Now coming to next very important part, I am going to explain about the preparation of haloalkanes. So, children, haloalkanes can be prepared by large number of chemicals, and first is from the alcohols, and this is the best way to prepare the haloalkanes either commercially or in laboratory. First is by using SOCl2. SOCl2, it is called as thionyl chloride. It is called as thionyl chloride, SOCl2. Now this method is best method. This is best method to prepare any haloalkane. Why? Because the product formed is almost impure. Why? Because SO2 is gaseous form, HCl is produced in gaseous form. The two byproducts, HCl and SOCl2, this SO2, they are gases, so they escape away, and as a result, this product is in almost pure state. So this is the best preferred way to prepare any haloalkane, that is by reaction between alcohol and thionyl chloride, and just slightly warming is required. Now second is by using red phosphorus. So any haloalkane can be prepared by taking red phosphorus and alcohol. Any alcohol, primary or secondary, it makes no difference. And so red phosphorus on heating, there is formation of haloalkane, HCl and chlorine gas is released. Then using haloalkanes. So haloalkanes can be, hydrogen halide can be used. Hydrogen halide can be used to prepare haloalkane. So HCl, HBr, HI, etc. So I am taking HBr in presence of anhydrous zinc chloride. This is Lewis acid, and as a result there is formation of this, and water is produced as byproduct. Then PCl3 and PCl5. So if we take PCl3 alcohol, so for this PCl3, so H3PO3 is produced as a byproduct. If you take PCl5, then there is this HCl and POCl3 are product as produced as byproduct. So this is there. Next will be from the alkanes and from the alkenes. See how. Now next second method is from hydrocarbons. Hydrocarbons, it can be from the alkanes or alkenes. So they can be easily converted into corresponding haloalkane. Like here, if you take any basic hydrocarbon, methane, ethane, propane, etc., so they on exposure with halogen in presence of ultraviolet light or sunlight, or you can say diffused light. Some energetic range has to be provided, and so we get mixture of hydrocarbons, and they can be further adjusted their concentration by changing the concentration, or they can be further separated by fractional distillation. Now coming to from the alkenes. Alkenes, they are solid in organic solvents, so like CCl4, neutral solvent. So when chlorine gas, this in gas is passed, so there is formation of, this is 1,2-dichloroethane. This is 1,2-dichloroethane. If you take the same reaction in presence of bromine water, or we take the liquid bromine, so this takes place at room temperature. This reaction and this reaction takes place at room temperature. Just past the ethene. There is formation of this, and so this bromoethane. And so this is a very simple way. So similarly, this is not for any commercial, just for the theoretical point of view. Now coming to next, preparation of haloarenes. And also haloarenes, they cannot be prepared like what we have prepared in case of haloalkanes, because of the difference in nature, difference in the properties. And so first is electrophilic substitution reaction, because arenes or any aromatic compound, it is highly stable due to presence of delocalized electrons. These have delocalized electrons. In the ring there is a pair of delocalized electrons. So like this, and here this is one ring, here is other. So it appears to be highly reactive, but actually arenes are highly stable and they do not undergo reaction like the other alkanes. So first, by electrophilic substitution reaction, so we take any direct addition, direct halogenesis is not possible, or due to this, direct halogenesis is not possible. And so first we take any alkyl benzene, and then there is the addition of halogen, FeCl3 dark, and so we have this product. This is the side chain halogenesis. This is called as side chain halogenesis. It is not possible to add directly by this. Now second, this is very important reaction, Saint-Meyer reaction. It is Saint-Meyer's reaction. So this is benzene diazonium chloride. C6H5N2Cl, benzene diazonium chloride, BDC. And this presence of cuprous chloride, there is formation of this chlorobenzene. Other is Gatterman reaction. Gatterman reaction is second one. In Gatterman reaction, we take benzene diazonium chloride, and then we take the, this is again copper powder. This is copper powder. And we take the, we take concentrated HCl, and here we take, we get this. In place of this, we may take copper and then concentrated HBr. If you take concentrated HBr, so here we have the bromobenzene. So this is there. Now coming to this benzene diazenyl chloride. So this benzene diazenyl chloride, it is highly unstable and it cannot be prepared as it is. It cannot be kept. So it is prepared in situ. And so with this we take the aniline is taken and NaNO2 aqueous and HCl concentrated and temperature is 5 degrees Celsius. Then there is formation of N2Cl, benzene diazenyl chloride, and this is called as diazotization. This is called as diazotization reaction. Di means two, azo means nitrogen. Diazotization. So this aniline on reaction with aqueous sodium nitrite and concentrated HCl, temperature is around 5 degrees Celsius, and there is formation of this benzene diazenyl chloride. Why this so? Because diazotization reactions are highly explosive and benzene diazenyl chlorides are unstable. So this is their Sanger and Beckerman reaction. So this is about the preparation by the direct halogenation. So far we have prepared chlorides, bromides, but we have not prepared iodides. So actually, iodides are not prepared easily. Iodides are prepared by the exchange of halogens. Why? Because iodide has very larger size. Size of iodide is very large, and so it cannot be added as such. And it is only possible by the exchange of halogens. And this is very important reaction. This is name reaction, and first is Fingerstyle reaction. Fingerstyle reaction, and in Fingerstyle reaction we take this haloalkane like chlorobenzene, this chloroethane, but here it is there to take the sodium iodide, and in presence of dry ether there is formation of corresponding ions. Iodoalkane is obtained. Similarly, other is Schwarz reaction. It is also very important name. This is Schwarz reaction, and this is for the for the iodides or iodo, you can say iodo derivative. Iodo derivatives are obtained, and this is for the chloro derivatives are obtained. So here we take any haloalkane, chloro or bromo, or even we can take the iodo, but here metal fluoride like silver fluoride, or we can take the copper fluoride, and so there is version of corresponding fluoro derivative. And so this is about the preparation of the haloalkanes and haloarenes.